Hello, my name is Li Zichuan from Hunan University. Thank you for your interest in our paper. Let me introduce my paper, AShapeFormer. Let's begin. First, we will give you a short 1-minute preview. We propose a plug-and-play active shape encoding module named AShapeFormer, which can be combined with many existing 3D object detection networks to achieve a considerable performance boost. To the best of our knowledge, our method is the first to combine multi-head attention and semantic guidance to encode strong object shape features for robust classification and accurate bounding box regression. AShapeFormer mainly includes 3 submodules: ShapeFormer, SGM and CAM. ShapeFormer utilizes shape tokens and object scene positional encoding to ensure that the shape information is fully exploited. SGM samples more foreground points and suppress the influence of background points for a better object shape perception. CAM fuses the shape information enriched features with candidate features to provide candidates. From now on, we will provide more details about work. Taking VoteNet as an example, most voting-based 3D object detection techniques commonly follow a pipeline that aggregates predicted object central point features to compute candidate points. Such an operation produces 2 issues. 1. The candidate points contain position information, largely ignoring the object-level shape information. 2. Candidate points contain background points that may affect the performance of 3D object detection. As shown in the figure on the left, the vote feature is the center point feature of the object. They cannot accurately describe the shape information of the object, especially when the surface point of the object is far from the center. In addition, as shown in the figure on the right, background point features are mixed into the vote group, which will directly affect the results of classification and regression. Figures on this and previous pages are from VoteNet and Burnet. As illustrated in figure, the proposed AShapeFormer selects more relevant seed points, leading to more appropriate candidates that additionally encode the object shape information actively. Given an input point cloud of endpoints with XYZ coordinates, we sample seed points using a backbone. The sampled seed points are processed by a voting module. The seed and vote points are used by our AShapeFormer module. Within AShapeFormer, the Semantics-Guided module pays more attention to the foreground points, while ShapeFormer additionally incorporates object-level shape features with multi-head attention, also employing positional encoding. The Channel Attention module fuses the shape information enriched features with candidate features to provide candidates to a detection head that predicts the bounding boxes. To understand our active shape coding technology more intuitively, we first introduce a naive method. As illustrated in figure, we encode the object-level shape feature using the seed points located on the same object. The vote points belonging to the same object are much more compact than the seed points. Hence, using indices of the candidate local grouping is beneficial for grouping seed points into a cluster, which belong to the same object. To get a single vector representation of the object shape, a naive approach can be similar to the candidate point local grouping, i.e., using MLP and max pooling. In any case, candidate features and object-level shape features are distributed in different feature spaces. Hence, in order to fuse these features, we propose the Channel Attention module. As shown in figure, CAM consists of fully connected layers with sigmoid activations. It adaptively learns weights for the features in different spaces such that they seamlessly fuse in the later processing. We note that the naive object-level shape encoding method proposed in this section reasonably effective. However, the explicit contribution of shape information goes beyond that. In our experience, the naive method still suffers from 2 main problems. 1. It experiences loss of fine-grained information in the interaction of shape key points. 2. It is marred by interference of the background points. These problems are resolved with the use of the proposed ShapeFormer and the Semantic-Guided module, discussed below. We introduce a shape encoding module based on a multi-head attention, named ShapeFormer. As compared to the naive shape encoding method discussed in the preceding section, ShapeFormer allows stronger shape encoding. In a naive construction, one gets a single vector representation of the object shape with an operation like max pooling, inevitably losing fine-grained information. Addressing that, we prepend a learnable embedding, shape token to the sequence of point features, whose state at the output of the ShapeFormer serves as the object-level shape feature. In ShapeFormer, we must pay more attention to the relative positional relationships between the shape key points and the object centers. These relations allow us to encode shape information at object level. Therefore, we propose object scene positional encoding, which not only encodes the absolute position of the point cloud, but also enables object-level positional encoding. The background points in a scene affect local feature extraction, which inevitably affects the shape encoding adversely through the shape key points. Although foreground points are selected for voting during training, we cannot supervise them during testing. Therefore, we further improve our AShapeFormer with a Semantics-Guided module to alleviate the influence of background points and shape feature. Specifically, we feed the seed point features to MLP layers to predict the point cloud semantic segmentation score, which is proportional to the probability that the point cloud belongs to the foreground points. The segmentation score is used as a weight to adjust the contribution of different seed points on the shape feature. We use the same strategy to weight the vote features for better vote aggregation. The SGM module helps AShapeFormer reduce, or even eliminate the influence of background points on object shape perception, and better use the features of foreground points to encode more accurate shape information. We evaluate the performance of the proposed AShapeFormer on two popular datasets of indoor scenes, namely, ScanNet dataset and Sun or GBD dataset. The results on Sun or GBD are summarized in the table. As a plug-and-play module, our enhancements outperform the baselines by remarkable performance gains. For instance, we achieve an absolute gain of more than 3.5% and 1.7% for VoteNet and EmbedNet, respectively. This table summarizes the results on ScanNet 2. Taking VoteNet as the baseline, our method achieves remarkable 4.5% and 8.1% improvements at map at 0.25 and map at 0.5, respectively. Applying AShapeFormer to the more recent transformer method group free 3D, and RGNet also has a significant improvement. This figure is our qualitative comparison. These results demonstrate that applying our method to the baseline detector achieves more reliable detection results with more accurate bounding boxes and orientations. As compared to the baselines, our method can discover more missing objects and eliminates false positives. This is the visualization result of the Sun or GBD dataset. This figure visualizes the positive impact of the SGM module on seed point sampling and voting during testing. The first row shows the seed points and vote points without the SGM module. It can be seen that the seed points and vote points contain a large number of outliers. The second row shows that with the help of SGM, we find more foreground points, and the vote points are also more compact and closer to the center, which is beneficial to our shape encoding and vote aggregation. Then is our last section, the conclusion. We propose as a plug-and-play module to improve the performance of indoor 3D object detection by actively encoding shape information of the object. We sample the shape key points of the object and weight their features by guiding them with semantic information. We utilize multi-head attention to encode object shape features to avoid the loss of fine-grained information. Results show that our model achieves state-of-the-art performance when assembled with existing methods. Thank you for listening our presentation.